G'day everyone, welcome to the first Lubrication Explained webinar. We haven't exactly done this before, so we'll see if I can get all the tech recorded, all the tech sorted out. Now the first thing would be, Mohammed has asked a question whether the meeting can be recorded as he's on site now in Egypt. So welcome from Egypt. You're basically the exact opposite side of the world to what I am. Really good to have you here. So this recording will kind of like live on YouTube. I believe that because it's being broadcast to YouTube, at the end of this, it will be available on the YouTube channel. So if you haven't seen it before, it's called Lubrication Explained. So, like, subscribe, all that good stuff. Cool. Well, we've got a few people floating in with the Zoom webinar as well, and we're actually going live to LinkedIn, I believe, at the moment as well, although I haven't checked that. So welcome to the first webinar, and we are planning on doing a speed run of Machinery Lubrication Analyst Level 1. So for anyone who's unfamiliar, the ICML runs kind of a certification series. It began with MLT, so Machinery Lubrication Technician, Level 1 and Level 2, but to align with kind of the ISO accreditations for the other condition monitoring disciplines, which include vibration analysis and thermography, ultrasound. They wanted something which is like an LCAT 1 equivalent. And so we now have MLA 1, MLA 2, MLA 3, which would be the equivalent of your VCAT 1, VCAT 2, VCAT 3. All right, so our plan here is to go through MLA 1 in 2 hours. So it's going to be pretty rapid. Hopefully you can keep up. I think we'll have a few attendees that are sort of floating in a little bit. I know that there were some issues when I created a LinkedIn Live. It couldn't tell the difference between Australian daylight saving time and regular time, so I think there might be a hiccup and we might have some people floating in about an hour late, but yeah, it is what it is. Okay, so we are going to get started with the presentation. If you have any questions or comments, leave them either in the Q&A or in the chat box. I'll be able to bring up some questions live, so feel free to kind of jump in and interrupt if you have a burning question. And if I'm not already going to get to it in the materials, then I'll try to address it as we go along. Now, I've got a ton of material to get through, so let's kind of get started with it. All right, here we go. So welcome to MLA Speedrun. This is going to be very, very quick, and I'll see if I can hide these. Hide the pointer for the moment. All right, so MLA 1, as I said, Machinery Lubrication Analyst Level 1. So this is actually a really good introduction to the world of lubrication. Even if, hey, Randall. Randall says he's here from Costa Rica. That is very committed and very early in the morning. Thanks so much for being with us. Very excited that you could make it. So thanks to Randall. Okay, so MLA 1 speed run. We're going to get through this as quick as possible. The idea would be that this is kind of like a way that you can, refer back to this video in future. Maybe if you're going to take the MLA 1 exam, this would be kind of like a good cram session, if you like. I don't know if any of you guys used to do that at university. I know I certainly used to leave that kind of thing to the very, very, very last minute. All right, so let's get started. First of all, what is kind of lubrication? I would describe it as a very, very small niche that powers all the other niches, right? So if you think about what does lubrication do, lubrication is fundamental to pretty much anything that moves requires some kind of lubricant. And you know what? We're starting to venture even into things which don't move. So if you look at electrical contacts, for example, a lot of them are starting to be lubricated as well because of things like electrical wear. So this is an industry which is very unknown to a lot of people, but underpins a lot of the other industries. And that's what I find so interesting about it. It has this kind of outsized impact given the size of the actual industry itself. Now, why is it important to look at lubrication? So, for example, if you are in an industrial plant, typically about 1% of the maintenance budget will be devoted to lubricants, but poor lubrication can amount to up to 30% of a plant's total maintenance costs. There are all sorts of numbers around this, right? So when you look at the world's total energy consumption, about 23% of it is purely lost due to friction. and the work that we can do to either minimize friction or to minimize the let's say the material losses as a result from wear, we can make a huge impact not only on GDP but also on the climate. Right, so energy consumption obviously it underpins a huge amount of our modern economy. Now, when we talk about sort of maintenance and reliability and what is the place of lubrication in all of those, okay, it's important to distinguish the kind of different types of maintenance or the different types of reliability that are commonly talked about. So the first is reactive maintenance. You might have heard of this term. And to simplify it and to put it into kind of layman's language, I would describe this as being we fix it when it breaks. Now, there are all kinds of places that would operate in this kind of mode, right? I, for example, have a really old, beat up bicycle that I've been riding for many, many years. And my plan is simply to ride that thing until it breaks, right? So that would be an exact example of reactive maintenance. Preventative maintenance. This is probably where I would say that most industrial businesses are at the moment. And the idea is that we fix something at predetermined intervals. So think about your car. Maybe you change the oil every 10,000 kilometers. Maybe you take it in for a service once every 12 months. Maybe you do the service yourself once every 12 months. That would be an example of doing something on a fixed interval. So that's preventative maintenance. And then we've got predictive. And that's where I think a lot of the industry is trying to move to. And the idea is that we are going to fix a problem when we sense it. So this is where the condition monitoring comes in. If we can sense that there is an issue through whether it's oil analysis, ultrasound, thermography, and we can see the degradation on that P to F curve, then we're going to intervene. And then finally, you've got proactive, which is we're fixing the root cause of the problem before the problem even occurs. Now, it almost doesn't make sense, right? How can you fix something which hasn't even occurred? So, we're going to talk a lot about failures of machines which are due to contamination of lubricants. So if we know that contamination is the root cause of, let's say, 80% of hydraulic system failures, then anything that we do to address contamination is considered proactive. Now, for people who don't, are still trying to wrap their heads around this, I use the analogy of heart health, right? So if you want to keep your heart healthy, what is a proactive measure? Well, a proactive measure would be to eat a healthy diet, right? So we know that, a poor diet, lack of exercise contributes to poor heart health. So the better we eat, right, we can address the root cause before we ever have an issue with our heart. If we were to do predictive maintenance on our heart, the idea would be, okay, we're going to take a blood test every 6 months and we might monitor our cholesterol, right? We might do an ECG to monitor heart rhythms. And on the basis of that, we might then, prescribe drugs or something like that to intervene. Preventative maintenance, I think this is really very illustrative. Theoretically, if you were concerned about your arteries being clogged up, you could book yourself for a surgery every year and have it cleaned out. Now, that demonstrates the risk of doing preventative maintenance is that we over-maintain our assets. So obviously, by completing open heart surgery, there are risks associated with the surgery. In the same way, if we can over-maintain an asset, right? And there's been plenty of evidence, as particularly with things like infant mortality failures, that over-maintaining assets can be a significant problem. And then finally, if we are in a reactive mode for our heart health, we're just going to wait until our heart stops, hope that we can restart it and maybe get a heart transplant or something like that, right? So this is a way of thinking about the different kinds of maintenance. Now, where do lubricants fit in? Well, it can fit in any four of these different types of maintenance. And it should also be said that there is no correct way to do maintenance, right? So for example, we might have very cheap, very easy to replace assets, right? That it doesn't make sense to do any condition monitoring on them. A good example of this would be in food manufacturing plants, right? Those small motor-driven gears that drive conveyor belts. There might be thousands of them through a food manufacturing plant. It doesn't make sense to do oil analysis on all of them. It doesn't make sense to do maintenance on all of them. What it makes sense to do is wait until they fail because we have so much redundancy and we just keep lots of spares, right, in storage. So that would be an example where reactive maintenance can be the correct answer in certain circumstances. So that brings us to tribology. Now, tribology is just a fancy word for kind of lubrication engineering. It's actually a word that was invented in the 1950s, and it's the study of friction, wear, lubrication, bearing design, as well as the science of interacting surfaces. So like I said, basically anything that moves requires lubrication. Now, in our particular field, we're just talking about lubricants and greases, but tribology also extends to things like artificial limbs, right? How do you make a replacement ball and socket joint last for a very long time? Think about brake mechanics, right? So brake calipers, that's an instance where you want a high degree of friction and you don't want brake fade. You might have a scenario, for example, with the design, right, of actual gear teeth themselves and the gear mesh. That's also a form of tribology, but we don't cover all of those. All right, so you know, in kind of layman's terms, lubrication is the intersection of mechanical engineering, and we have some chemistry that we need to know. And then part of it, honestly, is I call it, making stuff up, but a lot of it has to do with our experience and the level of experience that we have and that we can bring to the table as well. All right, a fundamental concept that we need to understand when we're talking about lubricants and lubrication is this idea called the Striebeck curve. And here, what it says is, first of all, ignore Zn on P for the moment, and just imagine that as the x-axis as being speed. So initially, when something is moving very slowly, it has very high friction. That friction decreases, and then it starts to increase again. And there are three different kind of lubrication regimes. So the first is called boundary lubrication, and that's effectively when we have metal to metal contact. Then we have a mixed scenario where the fluid film is beginning to separate the two surfaces, but there's still a little bit of contact between the asperities. And then finally, you have hydrodynamic or elastohydrodynamic lubrication, where the surfaces are fully separated. All right, so how do we get there? How do we kind of arrive at the shape of this chart? Okay, imagine that you're pushing a block on the ground. And apologies for the sirens that are going on in the background. So if you're trying to push the block on the ground and there is full contact between this block and the surface of the ground, so maybe it's a concrete floor or something, what happens when you initially push faster? Well, we know that friction is actually only determined by the friction coefficient as well as the normal force. So in this case, it would be the weight of the block. So it's independent of speed, which means that initially the speed at which we move is completely independent of the coefficient of friction. But soon, if the floor is covered in oil, so everyone would have experienced this if they hydroplaned in a car, for example, or you've slipped on a greasy floor, as soon as you start to increase speed and you get hydrodynamic lift, right, what is going to happen is that that block is going to lift up into that liquid lubricant film, and no longer is the friction between the block and the floor, it's actually between the lubricant and the block, right? And that's going to rapidly decrease the amount of friction that is and the amount of force that's required to move that block. What happens thereafter is if I continue to increase the speed, it's kind of like a boat in water. You're having to push more water out of the way, and therefore that is going to slowly increase the amount of friction that is required to move that block. And so that's how we kind of derive the shape of that Striebeck curve. So going back to the Striebeck curve, remember we have boundary, mixed, and hydrodynamic lubrication. So boundary is where we have metal to metal contact. Mixed lubrication is where those surfaces are beginning to separate. And then we've got hydrodynamic, which is that full film lubrication. Now, Zn on P is this kind of dimension, like we put a number of the different terms together: viscosity, rotational speed, as well as load. So going back to our model, how can we kind of rationalize this? So if you can think of the weight of the block as being equivalent to the load that we have in a machine, what happens if the block gets heavier? Well, the whole curve would shift to the right because it requires more speed to generate that hydrodynamic lift. And it makes sense. If the block is heavier, it takes more speed to get it to rise up into that lubricant. Similarly, what happens if we increase the viscosity of the oil that's on the floor? We might be able to instigate that lift earlier. So imagine if the floor was covered in honey versus it was covered in water, right? Honey is able to support more load than water is. And so we bring on that full film lubrication earlier. All right. So these are the three different regimes. There's actually a fourth one, which I'll explain in a second. So boundary conditions are where we see very high load. It could be very, very slow speed, or it could be shock loads, which are causing the two metals to come into contact with each other. It's very typical of mining and construction equipment. So things like bucket pins on excavators, slew gears, very, very heavily loaded gears, anything where there's shock loading or there is a start-stop action, you'll generally find that we have metal-to-metal contact. Then we get into mixed lubrication. That's where we have transitionary kinds of loads. Maybe it's a little bit heavier, maybe you see a bit of shock loading, maybe it's an instance where the viscosity is optimized for a different part of the system, as is the case in engines, right? The cams and the lifters typically see mixed lubrication. Then we have hydrodynamic lubrication. That's very typical of continuous operation, relatively high speed, plain bearings. And then there's elastohydrodynamic. Now, what's the difference between hydrodynamic and elastohydrodynamic? In hydrodynamic, think of it as a plain bearing. So it's a cylinder inside of another cylinder, right? And we call those conforming surfaces. So the surfaces run parallel to each other. Elastohydrodynamic lubrication occurs whenever we have non-conforming surfaces. So think of a rolling element bearing, right? So the radius of the rolling elements is very different to the outer race, right? And as a result, we have non-conforming surfaces. Same happens within gears, right? They're non-conforming surfaces, so are cams, and there's a couple of other instances where we have elastohydrodynamic lubrication. Now, first of all, in hydrodynamic and elastohydrodynamic, it is the properties of the base oil which dominates the lubrication properties. And when we get into mixed and boundary lubrication, it's when the additives start to take over. Now, especially in boundary lubrication, it's pretty much all additive dominated. Now, if you were going to sit the exam, one of the things that you would need to know about the differences between these is effectively that when we have hydrodynamic lubrication, so remember that's like a plain bearing, the film thickness is what I would say is double-digit microns, so 10 microns and above in ballpark terms. If we had elastohydrodynamic lubrication, so that's where we have ball bearings, rolling element bearings. If we have cams or gears, typically it is single-digit microns. Now, to give you an idea of how big a micron is, a hair. Okay, I'm not an expert on hair, but a hair is about 75 microns. A white blood cell is about 25 microns, and the detection limit in your oil analysis is typically around 8 to 10 microns. So incredibly small tolerances we are talking about. So that's one of the things that absolutely blows my mind about the lubrication world. Think of a gas or a steam turbine. That full rotating inertia. A steam turbine could be 50 tons worth of rotating steel, and it is protected by a lubricant film which is invisible to the human eye. So it is, to take a quote from Castrol, it is very much liquid engineering, right? This is precision engineering, but done with liquids. Federico, thanks so much. I really appreciate that. It's always nice to hear that. All right, lubricants. They have 6 primary functions, right? Reduce friction, reduce wear, prevent corrosion, remove heat, remove contaminants, and just under the comment, transmit fluid power. Reduce friction and reduce wear are kind of two sides of the same coin. So if we can get separation between metal surfaces, and so if we can have let's say for example 2 gear teeth, right? If we have a gear tooth, then a film of lubricant, and then another gear tooth, it is obviously going to reduce friction, but also because we don't have the metals in contact with each other, it is also going to reduce wear. Now, the prevention of corrosion occurs in 2 different ways. Number 1, if something is covered in oil, by definition, it is not coated in water, right? And that's one way that we can prevent corrosion. The second way that we prevent corrosion is through the use of additives like corrosion inhibitors. Remove heat. Now, this is one that is often overlooked. So let's say, for example, a jet turbine oil, which is powering an aviation turbine, we usually say like 95 to 99% of its job is actually to remove heat away from the bearings. So imagine it has all those hot combustion gases running past the main bearings, right? We have to distribute that heat somehow. And actually, the oil system in those turbines takes the oil away and it dumps the heat actually into the fuel system. Think about an internal combustion engine. The flame temperature, let's say, for example, of natural gas is in the order of 1400 odd degrees Celsius, something like that, that actually exceeds the melting point of aluminium. So if we didn't have cooling oil hitting the underside of the piston crown, those pistons would melt, right? So removing heat is one of the key functions of an oil. Removing contaminants is a double-edged sword, because if something contains contaminants, we can use the oil to flush it away. We can also use grease to purge it out of the system. But if oil is contaminated, it can also bring contaminants, right, to the application. So removing contaminants is a double-edged sword. Finally, we've got the transmission of fluid power. Now, this is a kind of the special one out of the 6, because it really only applies to hydraulic systems. So hydraulic systems, think about like when you stamp your foot on the brakes in a car, when you apply pressure to the brake fluid, it then transmits that power to the brakes, right? So hydraulic systems operate in a very similar way. All right, when we talk about lubricants, when we think about them, it's almost like the states of matter. We've got solid, liquid, and gas, right? So solid lubricants, yes. Liquid lubricants, absolutely yes. Gaseous lubricants, not so much, although there are air bearings. We just don't tend to talk about them that much. And then finally, we have something called cohesive, which is not quite a solid and it's not quite a liquid. It is a grease in our world, right? So something which is a semi-solid is what we would call a cohesive lubricant. All right, a solid lubricant is one in which what we are trying to achieve is we like to have sort of, it's called lamellar materials. So they have atomically thin planes which have very low shear strength between them. So when we get this kind of rotation, right, the planes like to move across each other. One of the easiest ways to demonstrate that is actually by when you use a pencil, right? So when you're using a pencil, graphite is a solid lubricant, and it is layers of graphite which are sliding off and depositing onto the paper. So that's why the pencil motion is very smooth, and it's how you get the graphite to deposit onto the paper. And of course, graphite is a solid lubricant. Now, solid lubricants tend to be used in greases, not so much in liquid lubricants, because this is what happens if you put them in liquid lubricants. Over time, they do tend to separate out. So this is a time lapse. This is only about over a period of about an hour. That is a PTFE fortified gear oil, and you can see that there is considerable separation even just in that single hour. I've just going to pause here for a second because I've got a question from Frederico. What grease would you put in an electronic throttle body on the internal gear in order to not damage the electrical lines and sensors? Wow, that is some question. I'm not entirely sure I know the answer to that question. So I would have to know kind of like the electrical properties that you're wanting in that instance. So if you wanted something, for example, which is conductive, often you'll use a grease which has some graphite in it, because graphite is conductive, especially in the presence of a little bit of moisture. But in some instances with electrical contacts, we want them to be non-conductive, in which case we would use something with non-conductive solid lubricants. Sorry, that wasn't a perfect answer, but that's not my kind of like specialty, I guess. All right, as we move on, so what are lubricants made of? Fundamentally, there's only really, 2 different ingredients in them, right? So there's base oil and then there's additive, right? That's really the 2 different ingredients. Obviously, additives, there's a whole cornucopia of different types of additives, some of which we'll talk about. But effectively, when you're blending lubricants, there's really only kind of like 2 ingredients, right? Now, what are the proportions? It depends on the type of lubricant in question. So an engine oil, for example, would lean to a high additive package. Some of the marine diesel engine oils, especially when we were using high sulfur fuels, they could be up to 30% additives and had considerable amounts of detergents and dispersants in them. Something like a compressor oil or a modern turbine oil would be 99 to almost 100% base oil with a tiny, tiny, tiny amount of additive in it. So when we talk about base oil, what are we actually talking about? Okay, you've probably heard this term, mineral versus synthetic, right? So there's 2 different terms. So a mineral oil is, I always liken it to Lego. So a mineral oil, it comes from crude oil, which comes out of the ground. And crude oil is a mix of all sorts of different molecules. You've got paraffins, isoparaffins, there's naphthene rings, there's benzene type molecules, aromatics. And when we refine something, it is the exercise in sorting out those Lego piles into bricks of similar sizes and colors, right? It's effectively what we're doing when we do the refining process. A synthetic is one in which we take a known molecule and then we build that molecule. So we might polymerize it to make something that we want. So a polyalpha olefin, for example, is a synthetic which is made from a whole bunch of olefins that we stick together and we make a synthetic molecule. So that's really the difference between mineral and synthetic. You might have heard of this thing called the API groups. There's 5 API groups. The first 3, 1, 2, and 3, are mineral oils. So they originally were crude oils. They come out of the ground. They are refined, and then they are turned into mineral oils, right? And they are defined by their saturate content, which is basically to what degree is their single or double bonds, the amount of sulfur, and the viscosity index. Now, we haven't talked about the viscosity index yet, but effectively it is a kind of a measure of how thin does an oil get with increasing temperature. Now, the synthetics cover groups 3, 4, and 5. Now, group 3 is a synthetic in name only. So legally, you can market it as a synthetic in most markets. I think Germany might be the exception, but this is due to a legal ruling that occurred in 1999. There was actually a legal dispute between Mobil and Castrol. I won't go into it too much further, but basically group 3s can be marketed as synthetics, especially in the sort of the passenger car or consumer-facing world. In industrial, we tend not to call group 3 synthetics. We tend to call them mineral oils. Group 4s is a special group all of their own. They're called polyalpha olefins. They are the most common synthetic by volume in the industrial world. You'll see things like gear oils, some compressor oils made from PAOs, right? So polyalpha olefins get their own special group. Now, group 5. Group 5 is everything else that is not in group 1, 2, 3, or 4. So that does not mean anything about the performance because some group 5s are synthetic, some are not, right? So for example, a naphthenic mineral oil would be classed as a group 5. A vegetable oil would be classed as a group 5, but also a polyalkylene glycol would be classed as a group 5, or a synthetic ester would also be a group 5. So just because something is group 5 doesn't really tell you anything about the actual molecule itself. And unfortunately, this has, so Telmo has asked a good question, which I should raise now. So there are no mineral oils with viscosity below 80. No, so the viscosity index is not below 80. So the viscosity can be below 80, but the viscosity index is a kind of a measure of how much does the viscosity fall off with temperature. So just a little aside into viscosity index. What we want, right? If I could design the perfect molecule, I would want something that stays thick at hot temperatures. So think about an engine. What we want is something that is thin at cold temperatures so it can flow at startup. But once we start applying load to the engine and a lot of temperature, we want it to be thick. But Mother Nature gives us the exact opposite of what we want. And instead, most or all fluids thin out with temperature. So think about honey. It's really thick when you put it in the fridge. It's really thin when you heat it up on a stove. So now, how much it falls off is the viscosity index, right? So if it doesn't fall off as much, it has a higher viscosity index. But that's not the absolute kind of viscosity number. We'll explain viscosity in a second. All right. So let's keep going. Now, this has created a little bit of confusion, right? Because now in marketing terms, especially in the engine oil world, we have these ideas of like, oh, this is a semi-synthetic, this is fortified with some synthetic technology. All of that is actually meaningless and has got nothing to do with the API groups. They are all marketing terms. And different companies internally have different rules around what you can call a semi-synthetic. So for our purposes, the API groups, there are 5 groups. 3 of them are mineral, right? And then you have PAOs as group 4 and everything else is group 5. Now, where would you see these kinds of products, right? If you go from left to right here, I'm basically increasing the viscosity, right? So automatic transmission fluids are very light. Industrial gear oils tend to be quite heavy. So in general, the group 1s are available in a much wider viscosity band, although that is changing. There's a new group 2 coming out from ExxonMobil. and group 3s tend to be a little bit lower viscosity. So, for example, if I wanted to make a hydraulic oil, most of the hydraulic oils these days typically are probably a group 2 mineral, right? Group 4, though, a PAO, I can make in pretty much any viscosity I want, because remember, it's just putting Lego bricks together. And so if I just let the reaction go on longer, I can make a bigger molecule, and therefore it has more viscosity. All right, now what we're going to do is we are going to construct an oil, right? So starting from the beginning, right, what is the first ingredient that I put in my oil formulation? I need a base oil, right? So fundamentally, we need a base oil because what are we going to put the additives in, right? So we start with the base oil. Now, when I'm thinking about this, I say the first thing that I need to do is I need to protect the base oil. So what I put in is R&O. R&O stands for rust and oxidation inhibitors. So if I have oil, just like oil on a pan, right, when I heat it up, it can cook, right? That is the process of oxidation. So to prevent oxidation, I use antioxidants, right? And of course, we already talked about rust and corrosion. The next thing that I want to protect, right, in heavily loaded applications would be the actual machine parts themselves. So if I want to prevent against wear, I use anti-wear, right? A lot of the names, they're not very creative in this industry, right? So anti-wear. Now, if the pressure between the loaded surfaces gets too extreme for an anti-wear additive, I use an extreme pressure additive. So just think of it that way. If the pressure is too extreme, I use extreme pressure additives. So that's the next thing that I might add into my formulation if it's necessary. And then finally, if I have a very dirty application where I'm producing a lot of contaminants, I might want to put in something like a detergent, just like a dish soap, right, to help clean. Now, the key here is that we only want to use what is necessary. That's why we start at the top and we work our way down, because additives are the most expensive part of the formulation. So if we don't need to use them, we don't put them into the oil. So very large systems, right, that are closed, and I say closed because that means there would be less oxidation, right? That's just the base oil. Open systems, we put rust and oxidation inhibitors. If we see mixed or boundary lubrication, we put anti-wear. If it's higher shock loads, we put EP. If we have contaminants, there's detergents. So typical, heat transfer oil, usually there's a bit of oxidation inhibitor in those anyway. Stuff that is a typical R&O oil would be turbine and compressor oils, some circulating oils as well, because most of the time we're just protecting against high temperatures. Anti-wear is very typical of a hydraulic oil, right, where it's the pump that is seeing a lot of wear. EP is very common in gears, and then detergent you would see in engines. And so as you go from the top to the bottom, we are getting more and more additized. All right, what are these magic additives that we talk about? These are like the secret herbs and spices of the lubricants world. Okay, again, they do what they say on the tin. We are not very, we're not very creative in this world. So pour point depressants, they depress the pour point. We haven't talked about pour point yet, but it's basically when an oil gets so cold that it won't pour out of the jug, right? That is when you have reached the pour point, and it's because we get the formation of wax-type molecules at cold temperatures. We have spoken about viscosity index, right? That is the amount that it thins out at high temperatures. So to improve the viscosity index, we have viscosity index improvers, right? Amazing. Some oils will shrink or swell seals, right? Because there is an interaction between seal materials and the oils, right? Some they'll want to exchange with each other. So in order to swell seals, we use seal swell agents. Again, does what it says on the tin. If we want to inhibit oxidation, we use oxidation inhibitors. If we want to deactivate metals, right? The reason we want to deactivate metals is because they can cause further oxidation. We use metal deactivators. If we want to inhibit foam, we use foam inhibitors. Now, foam inhibitors come basically in two different flavors, right? We have silicon type foam inhibitors and we have polymethacrylates, right? So they're the two most common types. Then when you've got rust and corrosion inhibitors, again, does what it says on the tin, but they tend to bind to the surface and do things like exclude water from interacting with the surface. Detergents and dispersants. Detergents are helping to clean surfaces, right? And they'll also help to neutralize acids. Dispersants tend to agglomerate around soot, right? So if you get soot production in things like a diesel engine, right? Soot itself is not dangerous, but when soot particles start to connect together, they basically form abrasive particles. And so you want to deal with those with dispersants. Anti-wear agents, they are against wear, they are anti-wear. Typically, the most common anti-wear agents are phosphorus and zinc based. Zinc, phosphorus, and sulfur. So there's a molecule called ZDDP, Z-dialkyl dithiaphosphate. It contains zinc, sulfur, and phosphorus, but the phosphorus and the sulfur are what do all the hard work, right? That's the key there. And then we've got friction modifiers as well. So typically these are kind of lubricity enhancers. They're like fatty or acids that can help make things slipperier, right? So they are all of your secret herbs and spices of the lubricants world. So how would this look in a lubricant? Here's an example. If I've got a copper metal surface, this might be on an oil cooler or something like that. You can see that the surfactants want to bind to the metal, right? And they do that because if they are binding to the metal, then water is not in contact with the metal. And so we can prevent corrosion with that way. We have metal deactivators, and then you can see the dispersants kind of encapsulating these soot molecules so that they can't stick together. All right, now let's talk about the most important property of a lubricant. Now, when I ask people what are the three most important properties of a lubricant? The answers are viscosity, viscosity, and viscosity, right? Now, I'm not just saying that to be pretentious. It's the bulk viscosity of the oil, viscosity's relationship with temperature, and viscosity's relationship with pressure are the three most important properties. Okay, we've got two different types of measurements. There's absolute and kinematic viscosity. They are both the resistance to flow and shear, but with kinematic viscosity, it's resistance to flow and shear by gravity. So basically, if you take the absolute viscosity and you divide it by the fluid density, you get the kinematic viscosity. One is measured in centipoise, the other is measured in centistokes. Just fun bit of trivia. Stokes is named after someone called George Stokes. So there is no plural to that. So it's 1 centistokes. Right? Weird quirk of English. Okay, if we want to measure the absolute viscosity, basically we can put a spindle into some liquid lubricant, and if we spin it, we can measure the torque generated on the motor, and the viscosity will be proportional to the torque. With kinematic viscosity, right, all it requires is a U-tube, not the platform that we're streaming to today, but obviously you get a displacement in the fluid, and if you let it fall between 2 points, the amount of time that it takes for that liquid to fall is then also proportional to the viscosity. We use kinematic viscosity most of the time when we're talking about lubricants because it's quicker and easier to measure, right? So that's why we're mostly using kinematic viscosity. Now, the absolute viscosity is sometimes also called the dynamic viscosity. So that's another name that you might see for it. And there are a whole bunch of different ways that we can measure viscosity. The most common one you can see is we measure centistokes, so that's kinematic viscosity, at 40 degrees Celsius and 100 degrees Celsius. So most industrial oils will get measured at 40, most engine oils are measured at 100. There's the ISO VG grade, so that's the International Standards Organization viscosity grade. AGMA is the American Gear Manufacturers Association. SAE is the Society of Automotive Engineers. One thing to note here, 2000 centistokes is roughly the viscosity of like honey, and around 20 to 30 is probably about vegetable oil. So that gives you an idea for the kinds of viscosities. Right, diesel is about 6, gasoline is about 2. Now, note something about the SAE viscosity grades. Right, so a multi-grade engine oil would be something like a 15W40, which is very typical of a diesel engine oil. Because there are two numbers, that's a multi-grade. A monograde would be with one number, so an SAE 40, for example. Now, the other thing that you'll note is that with the crankcase oils, the numbers go up to 60, right? So you can have something like a 15W60, although those oils are pretty rare. And then the gear oils actually start at 65W. The idea behind this is that if it is a number that is 60 or lower, it must be an engine oil. If it is a number that is 65 and up, it must be an automotive gear oil. And that is basically to prevent them from being cross-contaminated in automotive workshops. So that's an interesting rule of thumb there. When you go to the ISO viscosity grades, it can seem a little bit difficult to remember which ones are which. Easiest way to do this is, first of all, look at that first number, an ISO grade of 10. The lower and upper bounds on that are just plus or minus 10%. Right? So you take the number plus or minus 10%. The other thing is that you don't need to remember all of these, right? There's a repeating pattern. 10, 15, 22, 100, 150, 220, 1000, 1500, 2200. Similarly, 32, 46, 68 repeats itself twice again. So these are the ISO viscosity grades, which are measured at 40 degrees Celsius. There's a little bit of an allowance between them, and that is mostly for industrial lubricants. When you've got the engine oil viscosities that I talked about before, they are measured. The W stands for the winter grade. So that is measuring the cold temperature performance of the oil. The regular number measures the high temperature performance. So that's both the 100 degrees Celsius kinematic viscosity as well as something called the HTHS, or high temperature, high shear viscosity, which is supposed to replicate what you would see in things like the cams and the lifters. Okay. Similarly, we also have a specification for the SAE gear oil grades. Now, there are some new grades which are coming. So there's a 0W16, a 0W12, and a 0W8. They're coming to the engine oil grades in the pursuit of more efficiency. All right, how am I going for time? We're going pretty good. All right. Still have to motor this along. All right, we talked about lubricants. Now we're going to talk about greases. So when we have an oil, we said that there are just base oils and additives. Now with grease, we introduce a third ingredient. So we have base oil, we have additives, and then we also have something called the thickener. That is the third component which makes a grease. Now the base oils are much the same. You can have all sorts of different base oils which go into greases, and if anything, there's more variety in greases than there are in lubricants. The additives, also very similar, although you'll note, I make note here of solid additives, which we mentioned tend to do much better in greases because they stay suspended, as opposed to in lubricants where they tend to fall out of suspension. So what exactly is the thickener and what makes a grease a grease? You can think of the thickener as being like a sponge. Now, grease aficionados will there's some problems with this analogy, but just bear with me for a second. If we have a kitchen sponge, right, it can contain water inside it. And when we put stress on that sponge, so we squeeze it, the water comes out. Now, if we take the stress off the sponge, it will then reabsorb water. That's exactly what a grease is doing. The thickener matrix is holding the oil, and when we place it under load, for example, when the bearing starts to spin, it squeezes out the base oil, and the key is the base oil is the thing which is doing the lubricating, right? So the base oil viscosity is just as important in a grease as it is in a lubricant. So this is what the thickener looks like under a scanning electron microscope. It's kind of like this massive internal fibers, which is helping to hold on to all of that oil. Now, you'll know that there is something called the NLGI grades. NLGI stands for the National Lubricating Greases Institute, right? So different consistencies of grease, right, kind of cover you for the different types of greases. So the 000, the 00, and the 0 are what we call semi-fluid greases, right? So they are starting to approximate the consistency of oil. But a 2 is your pretty common multi-purpose grease. Now, how is that actually determined? There is an ASTM test, which is called work penetration. It's effectively you're dropping a cone into some grease which has been worked. The further the cone falls, the less consistency the grease has. Now, there are different thickener types, right? And each have their strengths and weaknesses. By far, the most common type of grease thickener is the lithium greases. So between thickeners, we can split them out into soap and non-soap type greases. And within soaps, there are simple and complex. So a simple grease would be a calcium grease, a lithium grease, a barium grease, something like that. A complex grease, you'll see it aluminium complex, lithium complex, calcium complex. Now, each of those, as I said, has a strength and a weakness. So aluminium complex tends to be quite good across the board, except for things like low temperature pumpability, and it has problems with high temperature shear stability. The calcium greases have historically had issues performing at high temperatures because with a regular calcium grease, there is water inside the thickener matrix. So as you start to get to temperatures of around 70 degrees Celsius, they start to boil off and we lose our consistency. There have been concerns with barium greases and their toxicity. So one of the reasons why lithium is so popular is not because it's outstanding at anything, but because it's not terrible at anything. It's kind of, it's a jack of all trades kind of grease. So that's why lithium is about 70% of the total grease volume. Among the non-soap greases, you have things like the bentonite clays. They're also referred to as a non-melt grease. So if you were to see it in the exam, bentonite, clay greases are non-melt greases, obviously for very high temperature applications. Then you've got the polyureas. Polyureas are kind of have a reputation for not playing nice with the other greases, but they are very high performing greases. And then you've got the calcium sulfonates. The calcium sulfonates are, I've got a soft spot for them, mainly because the thickener is itself a solid lubricant. It contains these calcite particles, which can actually provide you some solid lubricant kind of built into the thickener. So they tend to be pretty expensive, but very, very, very good greases. All right. So where are the type of places that we would see different consistencies of grease? So in centralized grease systems, you can imagine in order to pump grease, you need something which is semi-fluid. So that's where you would see a 0 or a 00 or even a 000. Sometimes we even use 000 greases if we have a gearbox, for example, that is leaking. And we simply want a stopgap measure to stop fluid leaking out of the gearbox. Sometimes we put in a bit of a grease. Now, your number 2 greases are your high volume general purpose greases. Electric motor greases, for example, most of the wheel bearing greases are all NLGI2s. And you might use an NLGI3 if the electric motor is actually in a vertical orientation just to give it a bit more consistency to stop the slumping of the grease to the low side. Right, so that's an example of where we would use a 3. The 5 and the 6s are what we would call block greases. They have kind of like the consistency of a very hard cheese and are often used for very, very high speed bearings. Now, the color of a grease, right, has nothing to do with the performance of a grease, contrary to some popular opinion. So you might hear people say the blue greases perform way better than the red greases. This has got absolutely nothing to do with performance because the color is a dye. Most greases are a very boring kind of beige color when they're produced, and we all just put dye in for identification and branding purposes. There are some circumstances, though, in which the color of a grease is important. Take, for example, in the paper manufacturing industry. What we want is we want white greases because if a little bit of grease ends up on the paper calendar, we don't want to ruin the entire product, right? So that would be an example where the color of the grease is actually important to the process. All right, now we're going to go into the section where we talk about lubricant selection. And this is really about understanding what the lubricants do in different applications. So in engines, right, the engine oils are these incredible lubricants that have to do so many things at the same time. Look at what it has to do in all of these different functions. Not only that, but there are different types of lubrication. For example, the valves, that's a slideway because it's a linear motion. Same with the piston. The piston is moving up and down. That is a linear motion. Whereas the bearings are constantly rotating, right? So that's hydrodynamic lubrication. And if you think about how am I going to optimize the viscosity when there are so many different lubricated parts, this is where we kind of prioritize certain parts of the engine. So the crankcase bearings, for example, are the most important part of the engine because if we damage the engine crank, that is a very, very expensive maintenance exercise. So generally, the lubricant viscosity will be optimized for the crankcase bearings, right? And then everything else is a trade-off. So that's why we need things like anti-wear additives to protect the cams and the tappets because the viscosity is not optimized for them. They have heavier loads and therefore, we're going to see some metal-to-metal wear. And that's why an additive like ZDDP is important in engine oils. Now, I am actually working with a company that's working on an alternative to ZDDP. Have a look at the YouTube channel for a couple of those videos as we go through development of that. All right. When selecting engine oils, there are a whole bunch of different, what shall we call it, standards, right? So the API, for example, that you would have heard, the API CK4, API SN, API SP. The easiest way to remember which one is applicable to which, right? S stands for spark ignition. C stands for compression ignition. So one is for basically petrol engines, one's for diesel engines. Now, in actual fact, that's not what it stands for. The S stands for service and the C stands for commercial. So actually the API is basically kind of dividing it up between light duty and heavy duty engines. Okay, but the C category and the S category are really important because they are what we call backward compatible, right? So an API CK4 engine oil will be backward compatible to previous engines. Now, what do these classifications mean? Basically, it's kind of a minimum standard that the oil industry needs to meet in order to obtain this certification. Um, so API CK4 came around in about, I think it was about 2016. So modern engines will require something like a CK4 engine oil, and all of these tests are ensuring that these oils are up to standard. Now, in engine oils, API actually recently split their certification system between CK4 and FA4. FA4 oils are lower viscosity and they are not backward compatible, right? Now, in engine oils, we split. You're not going to need to read all of this, but basically there's a difference between API, which is generally for the American OEMs, and then you have ASEA, which is for the European OEMs, and they have a slightly different system, right? Different system, kind of slightly different requirements, but they generally map onto each other pretty well. Now, in an engine oil, this is a really good opportunity to talk about the lubrication of plain bearings, right? So remember, that's what we're lubricating in the crankcase of an engine. Now, most of these bearings will have some layers to them, right? So often there'll be some kind of tri-metal bearing. So you might have, for example, a copper alloy, a nickel barrier, and then a bearing overlay, which might be made of tin or something like that. So the steel backing provides the rigidity. The copper alloy has good fatigue strength, right? The bearing overlay has good anti-friction properties. And then you've got a nickel barrier, which prevents migration between the two metals. Now, when we are lubricating these and we have to make decisions over what kind of lubricant to use, there's all sorts of factors that go into it. So on the bearing design side, we've got the bearing size, radius, clearance, the friction coefficient, the speed, the eccentricity. And on the oil side, we need to decide things like the viscosity, the VI, pressure viscosity coefficient, temperature, the supply rate, how fast is the lubricant leaving. Now, all of these calculations are done by the OEMs when they go through the design process, but here are some rules of thumb that we can also use based on bearing speed and bearing temperature. It can give us an idea of the iso viscosity grade required. Okay. Now, you wouldn't need to know the specifics of that, I don't think, for the exam. All right, so that's plain bearings, which you would also see in some turbo machinery applications, right? So big gas turbines and compressors, they've usually got a tilting pad design, but they are plain bearings, right? And so that's how they are lubricated. Remember, plain bearings, hydrodynamic lubrication. So we got complete separation between the surfaces. Okay, in this instance, now we're going to talk about rolling element bearings. And the way that you might select the viscosity for a bearing, there are a number of different ways. This is kind of the, I think this is the SKF method. What you do is you calculate the mean bearing diameter. So it's kind of the average diameter of the bearing between the outer and the inner race. And you would go along these lines of constant speed. So for example, if I had a mean bearing diameter of 200, we scroll up to a speed of 2000 RPM, scroll across, that means the rated viscosity is about 7 centistokes. Okay. Now what we want to do is we want to use this thing called the kappa ratio, which is the ratio between the actual and the rated viscosity. So for example, if I looked at the actual application and I said, well, bearing is operating at about 50 degrees, I'm using an ISO 46, what is the actual viscosity at that temperature? That's 28 centistokes. Therefore, the actual over the rated gives me a kappa ratio of 4, right? And kappa ratio of 4 would suggest that I have complete separation between the bearing elements and the outer race, and would mean I'm in full film lubrication. As we start to approach a kappa ratio of 1, what that tells me is that I'm going to have to start relying on some anti-wear additives because I'm now in that mixed lubrication condition. And for very low kappa ratios, I'm in boundary lubrication. I'm going to need some EP additives, right? Even for my rolling element bearings. Okay, so that's a way that we can calculate the necessary viscosity. So SKF and NSK and FAG all have these calculators kind of built into their design process. Another question that you want to ask yourself with bearing lubrication is whether you're going to use oil or grease, right? Another decision that is often made by the OEM for you, but some of the factors might be that grease can generally go to, in some cases, can go to higher temperatures than oils, but it can handle lower speeds. Now, we didn't talk about this thing called the DN factor. The DN factor is that mean bearing diameter multiplied by the rotational speed. So you can imagine if you have a big bearing, big bearings tend to have slow RPMs, right? So large diameter, but low RPM, whereas small bearings tend to be small diameter, but high speed. So the DN factors tend to come out roughly equal, right? Now, obviously with grease, the reason why we can't go to very, very high speeds is because we are having to push the grease thickener out of the way. So as the rolling element is coming around, that thickener is having to be pushed out of the way, and we can generate too much heat. An oil, right, has the advantage of, number one, it's able to move out of the way very easily, but also we can have a circulating system such that it takes heat away from the bearing. A grease is not able to do that. So that is something to consider when you look at oil versus grease lubricated systems. All right, now let's move on to gears, and we'll start with automotive gears. You might have seen classifications or ratings called API GL, so API gear lubrication. Technically, there is GL1 through to GL6, right? But for all practical purposes, GL1, 2, 3, and 6 are actually defunct. Okay, so now you'll only see GL4 and GL5 lubricants. GL5 lubricants tend to be more heavily additized than their GL4 counterparts. And then we also have the MT1 classification, which over the page is probably more stringent. But the most stringent one at the moment is the SAE J2360, which is basically a combination of GL5 as well as MT1. So if you had to say, where would you use these, right? Broadly speaking, manual transmissions, you probably only need a GL4. As you're starting to get up into axles, GL5, MT1, and then some axles, the relative performance gets higher. Now, industrial gear oils, on the other hand, right, we can split them out. Now, remember when we talked about formulation, we start at the top with a base oil, then we add R&O, then we add anti-wear, then EP, right? So these are talking about the types of oils. So we can have industrial gear oils which just have rust and oxidation inhibitors in them. We can have industrial gear oils with extreme pressure additives. And then we can also have industrial gear oils that are what we call compounded. So they contain friction modifiers inside them. Now, how would you choose between them? So basically, it depends on the gear type. So as we go from the left to the right, these gears have more or less sliding action. So if you think of a spur gear, so that's straight cut gears, when they rotate relative to each other, the motion at the point of contact is mostly a rolling motion. Whereas a worm gear, right, looks like a spiral. For the most part, it is sliding against the face of the other gear. So what we want in general, right, is for most straight cut all the way through to hypoid gears, we are mostly requiring EP. But for worm gears, the reason why we generally do not use EP additives is because for the most part, the wheel is usually made of some kind of softer yellow metal, right? And EP additives, which remember are mostly sulfur-based, will often cause excessive corrosive wear of those gears. So that's why in general we use these compounded lubricants. Sometimes we'll also use a PAG, a polyalkylene glycol. Now, just a note on PAGs, and again, if it ever came up in the exam, the thing about PAGs is they have extremely good performance, very good oxidation stability, and they have a very high degree of lubricity. The challenge with PAGs is that they don't play nice with the other lubricants. Like they tend to be quite incompatible, especially with things like the PAOs. So they're not very miscible. Greg, let me just bring that comment up. So most gearboxes use ordinary sulfurized hydrocarbon oils. What about manual gearboxes in automobiles that use engine oil or automatic transmissions, and even some manuals that use ATF? Oh, okay, good question. Yeah, so sometimes what we will see is oils used in different circumstances. Classic example of this is actually the tractor hydraulic fluids. So if anyone has worked around farm equipment, there are some, let's say, for example, tractor hydraulic fluids for, let's say, Massey Ferguson or Case New Holland, where we have a product that is a unified system for the hydraulics, as well as the gears, as well as the transmission. So in that case, we are kind of over engineering the lubricant so that it can do all of those things at once. Now, there are actually a class of lubricants called supertractor. So STUOs, they're called supertractor universal oils, which can not only lubricate all of those components, but they also function as the engine oil as well, right? And so remember, when we said what oils are the most highly additized, the most highly additized oils tend to be the engine oils, right? Because they contain not only the R&O, they contain the anti-wear, they also contain detergents. So generally, an engine oil will actually be over-engineered for something like a hydraulic oil application or even for some gears, right? So that's why in some cases, you can get away with an engine oil in a gearbox. In fact, that's one of the big splits between mobile hydraulic equipment and industrial hydraulic equipment, which we'll get to in a second, is that mobile hydraulics, traditionally, they've used something called a cutback engine oil, which is basically you took an engine oil, deleted out 50% of the additive package, and said, well, that's good to use as a hydraulic oil now. Okay, so hopefully that kind of answered the question. All right, so let's go on. The typical kind of what do we call it? Formulations for a lot of these products, right? So you don't need to know the details of this. What I'm trying to stress here is that the additive packages which go into the automatic transmission fluids tend to be much more heavily additized than the industrial counterparts. And among the additives, for the most part, it's anti-wear or EP. And then amongst the others, you'll have your corrosion inhibitors, your antioxidants. Occasionally, you might see some detergents and dispersants and things like that. Pour point depressants, VI improvers. All right, so that's the gear oils. Then we move on to the hydraulic oils. Now, this is a typical hydraulic circuit. And here, right, think about what a hydraulic oil has to do. Uniquely among all the lubricants, it needs to transfer power, right? That's the one big difference between the hydraulic oils and all of the other counterparts. But when we're talking about protection, what are we primarily protecting? We're primarily protecting the pump. The pump is where most of the wear occurs. So if you think of, for example, a gear pump, right? You've got the gear mesh, right, which is potentially going to wear. In a vane pump, right, it is the sliding action of the vane on the outer casing. If you think of what other kind of pumps, piston pump, right, it's the action of the pistons against the swash plate where most of the wear occurs. So that's why hydraulic oils tend to contain a fair bit of anti-wear additives. Now, in terms of selection for hydraulic oils, right, I like to use this kind of matrix where we have on the bottom axis the viscosity index, and on the y-axis whether it is zinc-based or zinc-free. So as we go from left to the top right, we increase the amount of cost that is involved in the formulation, right? So on one dimension, we're talking about the anti-wear properties and the keep clean performance. And on the x-axis, right, we are talking about the temperature range that we can use the hydraulic fluid over, as well as the hydraulic efficiency. Now, this is one of those cases where more expensive is not always the correct answer, because I go into basically a lot of sites, and if you were to say, how much hydraulic oil do you spill? You know, they tend to spill a lot. Like, there's a lot of blown hoses, and there's a lot of hydraulic oil that ends up on the ground. So before moving to any kind of premium hydraulic oil, the key thing is to fix up those leaks first, partially because it's a waste of money, partially because it's an environmental disaster waiting to happen, right? So in this bottom left-hand corner, if you are seeing high loss systems, or if you have a system with mild temperatures and a very large reservoir, you might go with a very standard VI zinc-based product. The higher viscosity index is very typical for a lot of industrial hydraulics, where you want that sort of increased hydraulic efficiency that comes with a high VI. Zinc-free, so the ZDDP molecule is a bit toxic, right? So if you are, let's say, for example, a crane working over a waterway, that might be a case for a zinc-free solution. And finally, right, in the top right-hand corner, where we want the premium hydraulic oils, is where we want low toxicity. We want a wide temperature range that we get from the VI, also the keep clean requirement. So at high temperatures, that zinc molecule that we talked about actually breaks down and it turns into sludge. And so that's a reason why we might not want to use a zinc-containing hydraulic oil. All right, separate to that, we also have the environmentally aware lubricants, right? So for environmentally sensitive applications, they tend to be based on synthetic esters. And then we have the full synthetics, which are for extreme temperature applications. So think about wind turbines in Arctic conditions, for example, might need something where we get very low wax formation at low temperatures. And so we have a very, very, very low pour point. All right, now, you're not going to need to know all of these, but these are all the different hydraulic standards. So we have the DIN standards, the ISO standards. They relate to the kinds of oils that we're talking about. Now with hydraulic oils, there are some pretty exotic ones out there. For example, the phosphate esters for the hydraulic control systems on turbine oils. So the phosphate esters we haven't talked about so much, but the phosphate esters are a specialized chemistry, which is a fire retardant fluid, so an FRF. Some of the PAGs can also be fire retardant, right? And instances where we might want to use these is where we need something called factory mutual approval. So there's actually a company over in the US where you can lower your insurance premiums if you're using their approved fire retardant fluids. Now, I've just got a quick question from Greg again. Does the zinc-free chemistry of automatic transmission fluids serve any purpose in industrial hydraulics? Honda and Toyota use ATF in the steering hydraulics. Yeah, so why would you want to go with the zinc-free formulation? So like I mentioned, sometimes at high temperatures, the zinc molecule can actually break down and you get the formation of sludges. So in hydraulics, where is that really important? Well, in the servo valves, right? So servo valves have very tight tolerances. And if we start to have either contaminants in the form of particles, or if we get sludge that is from the breakdown of additives, that can start to interfere with things like the operation of hydraulic servo valves. So that might be an instance where you have very, very small clearances where you would want to use a zinc-free solution, right? Now, we do have alternates for it. So you can have non-zinc anti-wear additives, right? There's the new one that I talked about, but there's also just the plain phosphorus-containing anti-wear additives. Now, just going back to the hydraulics, but thanks for that question, Greg. So when we talk about the different OEM standards, right? There's Vickers and Denison and AFNOR and Pocklane and all that sort of stuff. The kind of the gold standard is kind of the Bosch Rexroth one. So if you see Bosch Rexroth approval, that's sort of become the gold standard. And the only reason for that is if you plot all the tests on a chart of pressure and speed, then the Bosch Rexroth one is the one that sort of is the outlier in that it exerts the highest pressure on the oil as well as the highest speed at the pump, right? So that's selection for hydraulic oils. Okay, so that's the selection component of MLA 1. I know we're absolutely blasting through this, but it was a speed run, and I'm going to take a quick drink of coffee here. Oh, and Pham says hi from Vietnam. Hi, Pham. Thanks so much for joining us. I know it's actually pretty late in Vietnam, so appreciate you staying late. All right. Okay, so that's lubricant selection, which we absolutely blew through. Now what we want to start talking about is oil analysis. And where we start with oil analysis, we have to start with taking samples. So there is a whole science around taking clean samples, right? Representative samples. And that's our objective. When we are taking a sample, which is how most oil analysis is done, right? We take a sample and we send it off to a lab. The objective is that we are trying to take a representative sample. And this has to do with how we take the sample, but also where we take the sample and when we take the sample, right? So we want it to be as representative of the system as possible. Now, where does oil analysis kind of fit into the overall picture of maintenance? Well, if we are obtaining wear information from a sample, that is kind of predictive, because as we start to see the wear increase, right, we can make interventions. It's also proactive, right, because we can make assessments of the fluid condition and we can intervene, whether it's to do an oil change Or in some cases, if we need to replenish additives, there is something called a bleed and feed. So let's say, for example, you needed a bit of an additive top up and I had a 1,000 litre system. You could bleed off 100 litres, top up with 100 litres of fresh oil, and that would be a way to treat the system. Finally, we also have measurement of the amount of contaminants that are in the oil. We know that, for example, roughly 80% of hydraulic system failures are down to contamination of the oil. Right? So contaminants are a really important thing when it comes to lubricants. So that is considered proactive. So think about our sample. We're trying to take a representative sample. One of the things that helps us take a representative sample is how clean is the actual bottle itself. Right? There are actual formal definitions on what is clean, super clean, or ultra clean, and it's the number of particles that are more than 10 micron per mil of bottle size. Now, another thing which is really important to do before we've even taken a sample is to know where we are taking the sample from, the oil type, the oil viscosity, the asset number. All of this information needs to be cataloged. Otherwise, the actual result itself is almost meaningless without context. Now, why have I put a newspaper behind the sample? Even when we take the sample, right, the first thing that we want to do is make a visual inspection of the sample. And in some cases, we might even want to smell the sample. Different oils smell different, right? But a visual inspection, is there any visible sediment in it? That's a bad sign. Are there any visible metal shavings? That's a really bad sign. But can we read a newspaper behind it is a pretty good indication of how much water is in the sample. So if it is clear enough to be able to read a paper behind it, then usually that is relatively low levels of water. Again, this is all kind of rules of thumb, which can be verified then by an actual lab analysis. All right, so how do we want to take samples? The first way that most people are probably familiar with is taking it at the sump, right? Now, taking it at the sump is an unideal location to take oil samples from because any material which is on top of the sump plug is going to end up in the container, and therefore it is not representative of the rest of the oil system. So in some cases, we have no choice, right? There is no other place to take the oil sample from, in which case, drain off a bit of volume to allow those contaminants to be flushed out, and then take a sample midstream. That would be an example of taking from a sump. Then we also have drop tube sampling. A lot of people would be very familiar with this if you're sampling from gearboxes or hydraulic reservoirs, where all you have is a hatch to open at the top. What we want to do is we don't want to take a sample where the bottom of the tube is right at the bottom of the gearbox, because again, we might be sucking up a whole bunch of sludge and sediment which has remained at the bottom of the gearbox, and that's not representative, there's that word again, it's not representative of the rest of the oil system. Then we also have sampling ports. Now these are in many ways the most ideal, mostly because we are always taking a sample from exactly the same place. That is highly desirable, right? So we have a probe that goes into what we call the live sampling zone. So an area where we have turbulent flow. And depending on whether our system is pressurized or non-pressurized, we might have something called a mini mess, which is basically a one-way valve. If the system is pressurized, we can simply push on that one-way valve and oil will come into our sample bottle. Or alternatively, we can use a vacuum sampler to draw a sample. Now, there's a couple of other things that we need to know when we're taking samples, and this would also be relevant for the exam, right? There is a certain amount of volume that we want to flush, right? So if you look at, for example, the little bit of the probe that is going into the gearbox, that would be called dead volume, right? Because any oil that is in there is not flowing. So we want to ensure that we are flushing about 5 times that volume so that we have no kind of like dead volume oil in the actual sample bottle itself, right? So that's one thing that's really important. The other thing that's really important, we always want to be taking oil from the live zone. So that's an area of turbulent flow, which is representative of the entire oil system. So that's kind of like the sampling methods. But not only that, where we sample can be extremely important. And what we are trying to maximize is what we call data density. So what is the important information that we are trying to derive? because in, let's say, for example, a circulating system, which I have here, the amount of wear materials may differ depending on where I sample from. So, for example, generally what we would say is that the primary sampling point is going to be after the pump and before the filter. The reason for that is because the filter is going to capture a bunch of those wear materials. So in a hydraulic system, if we want to see what kind of wear the pump is experiencing, we need to do it after the pump and before the filter. But alternatively, if I think that one of the bearings is wearing, then I would need to sample downstream of the bearings before the reservoir, right? So where we sample is also going to have a very large impact on the results. Alternatively, maybe I had this kidney loop filtration system, which you can see off on the right here. If I want to determine how clean the oil is in my reservoir and how well is my kidney loop filtration system cleaning the reservoir, then I might need to take a sample from there. Now, when to sample? In some cases, right, I would say most industrial customers that I work with have a generic rule for how often they sample. So it'll be once every 3 months, or all our assets once every 6 months. Technically, the more critical an asset is, the more frequently we should be sampling to maximize the data density. Now, when we do sample and we send it off to the lab for analysis, what are we testing for? We are testing for things like the breakdown of the oil. So oxidation is something that affects the oil. Like I said, it's like the oil cooking, right? It cooks with heat and exposure to air. So oxidation, as it implies, is the exposure of oxygen to the molecules, right? And it will cause the oil viscosity to increase slowly over time. It also causes the acid number to go up because we get the formation of acids. When an oil oxidizes enough, you'll get the formation of deposits and you'll also get oil darkening. It's like if you leave oil on the pan for too long. And there's a general rule which we use called the Arrhenius rate rule, which says that for every 10 degrees Celsius above 60 degrees Celsius, the life of a lubricant halves. So if we go from 60 to 70, halve your life. If you go from 60 to 80, we decrease the life by 75%. Right? So temperature plays a very important role in how long a lubricant can stay in service. Nitration is kind of like oxidation, but with nitrogen instead. And so it happens at much higher temperatures because to break the nitrogen molecule apart requires a lot more energy because it's triple bonded to itself. You'll often see this, well, not often, but you'll see this in things like combustion engines, right? Again, you'll see the formation of acids. You'll also see some varnishes occur. Now, thermal degradation is an actual breaking of the base oil molecule at very, very high temperatures without oxygen involved. So this is a breaking of the base oil, and it tends to happen at temperatures in excess of 200 degrees Celsius. So now we're mostly talking about things like thermal systems and heat transfer systems, right? So sometimes it will cause the viscosity to increase. Sometimes it will cause the viscosity to decrease. So it's a little bit more difficult to pick up on thermal degradation. All right, another test that's done to measure oxidation, right, is FTIR. So effectively what we're doing is we're shining an infrared light. Different molecules inside the oil will absorb different wavelengths of infrared light. And so we can use this to assess how much oxidation has occurred, how much nitration, how much sulfation. We can also measure total acid number and total base number using the FTIR now, even though there are also titration methods to measure this. We can also get a measure of the water, the soot, as well as the glycol. Now note that soot in the field can also be measured by what we call the blotter spot test. So it's almost like putting a blob of oil onto kind of like a little piece of paper, and we see how much it disperses. And it gives you a measure of the dispersancy of the oil and how much soot buildup there is. I'm just going to skip over this for a bit. Okay, the other thing that can happen is that if we get water contamination into our oil, it experiences something called hydrolysis. So this is the interaction of both oil as well as additives with water, and it will cause an increase in the amount of acids in the oil. So we test this by something called the Coke bottle test, where basically you mix oil, water, and you have a copper strip inside. And as the acids build up, they'll start to eat away at the copper. And so by looking at the copper appearance, as well as the amount of mass that's lost off the copper, then we can get a measure for how much hydrolysis, or how susceptible an oil is to hydrolysis. Speaking of additive depletion, additives can deplete in a number of different ways. So there is decomposition, which means that they basically break down in service, right? There is also separation. So let's say, for example, some of the antifoam additives, for example, under very, very cold temperatures, and if you store them for very long periods of time, they can settle out of the oil. In some cases, if we use filtration, which is way too fine, we can actually remove some of the additives out of the oil, right? And in some cases, they could evaporate at very, very high temperatures. Then there's adsorption, right? In some cases, adsorption is desirable. So for example, ZDDP, the anti-wear additive, is designed to bond to metal surfaces under high temperature and pressure. We want that, right? That's the whole purpose of an anti-wear additive, but it does cause the additive to be consumed. Separately, if we get water, something called basically water washout of additives, is that an additive is dumb. It can't tell the difference between a metal or water or a particle. And so if it sticks to water, it's not really doing its job correctly, right? And so that's one of the reasons why we're trying to keep water out of our lubricants. Now, the most frequent test, well, I say most frequent, it's actually one test which tests a whole bunch of different metals, is something called ICP. There's a couple of different methods for doing this. There's ICP AES, which is atomic emission spectroscopy, and there's also RDE, which is rotating disc electrode. For both of those methods, and for the purposes of the exam, we would basically say that it can see particles up to about 10 microns in size. And that's really important because some wear modes will generate wear particles which are larger than 10 microns, which won't be picked up by this test, right? Also, it is important to know what is your machine made from, because if we say that we are starting to see silver in our oil, now either we're about to become rich or the silver has to have come from somewhere, right? So where could silver come from? Well, silver traditionally was used in a lot of engine bearings for the rail industry once upon a time. So there were a lot of zinc-free engine oils in the rail industry because zinc would have interacted with the silver. Some of the other ones, right? Magnesium, for example, is a very common detergent additive, but you would need to know that. Something like calcium, right? Calcium can be a detergent, but it can also be a contaminant. So if I work at, let's say, for example, a cement mill, right? Going to be a ton of calcium dust. So knowing where all of this stuff comes from is going to help us diagnose what's going on with our equipment. Okay, water ingress. Now, water is so pernicious to oils, and water can get in. The water just is annoying, right? Because it gets into oil no matter how hard you try to exclude it. And part of that is because a lot of oils are what we call hygroscopic. That means that they attract water. In fact, they attract water so much that they'll pull the humidity out of the atmosphere. There are basically 3 different types of water in oil. There's dissolved water, which is not super harmful, and there's not a whole lot that you can really do about it, right? It's just dissolved in the oil. There is emulsified water, which is when you form an emulsion. I'll explain that in a second. And then there's free water. Free water we kind of like in industrial systems because if we can get a separation in the reservoir between the oil and the water layer, it's very easy just to drain off that water, right? Now, some oils like to readily separate, some do not. And we have a whole bunch of different methods, which I've put here, which allow us to remove different kinds of water. So the most difficult type of water to remove tends to be the emulsified as well as the dissolved water, right? And the most reliable way of removing water is vacuum dehydration. So effectively what you are doing is you are lowering the pressure inside a vessel So you're lowering the boiling point of water, and then you are able to boil that water off. That's the most reliable method. Unfortunately, it's also the most energy intensive and therefore probably the most expensive, right? But we can remove water. Now, this demulsibility measurement, which is ASTM 1401, basically you put oil and water in equal amounts into a cylinder, you mix them up, and then you see how readily do they separate. Not only how quickly do they separate, but at the end of the test, is there any emulsion that remains, right? So that's the kind of test for it. All right, the reason why water is so frustrating is because when water and oil mix, they don't play nice. So you would think that if you mix two fluids, that the viscosity of the mixture should be the average of the two fluids. But in emulsions, that's not the case. So if you think of, if I mix vegetable oil and water with a little bit of egg, what I get is mayonnaise. And mayonnaise is significantly thicker than both oil and water, right? So this is what emulsions can do to viscosity. And I've seen gearboxes, for example, that end up with oil starvation events because they can't circulate the oil enough. It also, right, plays into sometimes our formulations. So in a steam turbine, you would expect that the oil will come into contact with water. Therefore, we need to make sure that we can separate out the water and the oil as much as possible. With a gas turbine, that's not so much the case. Gas turbines also tend to experience higher oil temperatures, so you will often boil that water off, right? So that means that in a gas turbine, we can put detergents in because detergents tend to mess with emulsions. All right, we don't really think of it as being a contaminant. Another contaminant is air. And there are a number of different forms of air, just as there are different forms of water. So we have dissolved air, which you can't see. There is entrained air, which is bubbles that are inside of the oil itself. You then have foam, and then there's free air in the headspace. Now, which of these do you think is the most kind of dangerous, right? Most people generally say foam, and that's because it's the most visible. If you've ever had a foaming problem in like a gearbox or a hydraulic pack and had foam spilling out the top, it's very obvious that you have a problem. In actual fact, I would say it's the entrained air which is the most problematic, right? Entrained air, if it gets sucked into a pump, can cause cavitation issues. In hydraulic systems, for example, you can end up with sponginess, right? Because air is compressible where the oil is not. So it's almost like getting air in your brake lines, right? So you stamp your foot on the brake and nothing happens, right? So foam is necessary, in fact, because we want in the reservoir the oil bubbles to rise to the surface where they become foam, and then we want the foam to break. That's the key. We need the foam to break, right? And it would release air back into the headspace. Now, Gopal has just asked an important question: how to distinguish between dust ingress and the seal or the gasket leaching if it's silicon based into the oil? Fantastic question. So this goes back to our ICP, right, of wanting to know if I see silicon, right, gasket materials can be made of silicon, sealants can be made of silicon. Unfortunately, silicon is also a major component in dust. Now, one thing is that when you have dust ingress or dirt ingress, most of the time, most dirt is not silicon alone. It's usually a combination of silicon and aluminium. Now, wherever you are in the world, the proportions of those will vary anywhere between 2 to 1 and I think about 12 to 1. But what is important is that for the purposes of trending, if you take a number of oil samples, if you see silicon and aluminium increasing in what we call a lockstep trend, so they increase together, that is indicative of the fact that it is dirt ingress and not a gasket, right? Where you would just see pure silicon increasing and nothing else is increasing at the same time. So hopefully that answers that question. All right, so we also just talked about air contamination. Now let's talk about the most common type of contamination, which is particle contamination. And to understand that, we need to understand the ISO cleanliness code. So this is the number that you'll often see on your oil analysis report, where you see 3 different numbers. It might be 20/14/11. So what this is a way of counting. So let's say, for example, the ranges are particles more than 4 micron, particles more than 6 micron, particles more than 14 micron. So let's say, for example, in a 1 mil sample, I've got about 8,000 here. That would be a class of 20. If I have 95 that are greater than 6 micron, that's 14. And then there's 11 for 11. So this is how I would get my numbers. Now, a couple of things that are important about this scale. When you look at the lower and upper limits, every time I go up by 1, the numbers double. So if I move from 20 to 21 in my ISO code, that is doubling the number of contaminants. So if I go from 20 to 22, that's 4 times the number of contaminants. So it's an exponential scale. It's not a linear scale. And this is a way that we can measure particulate contamination in our oil. Now, there are a number of different ways to actually physically measure particulate contamination in oil. Let me just go back to that previous slide. So the first one is what we would call particle count by optical microscopy. So we are literally making a filter patch and looking at it under a microscope, and a very trained practitioner can give us an ISO code based on that. We also have automated particle count by light extinction, where we're either shining a light or a laser through the oil sample, and based on the shadows that it casts on a detector, we are getting a measure of the particle count. Unfortunately, air, sludge, additives, water can all cast shadows, and therefore we can get a falsely high reading as a result. Then there is also the patch test. Now, this is a little bit like particle count by optical microscopy, but in the sense that we are doing it in the field, and we are literally just making a patch and then observing it. Maybe the color are there any visible sediment? And we might weigh the patch, and that could be a measure of the contaminants. There's also the pore blockage method, which we allow an oil to go through a membrane, and based on the increase in pressure, we can get an idea of the ISO code. There's also something called laser net fines, right, where we are actually characterizing the types of particles that we see in the detector. So now that we know how to measure particles, how the hell do you remove them, right? There are a number of different types of filters: surface filters, depth media, and magnets. Now, magnets generally you'll find on like a sump plug, and that's just there to collect wear debris. However, monitoring the amount of wear debris that is collected on the magnet can be an important data point when we are doing condition monitoring. Surface filters are basically a mesh, right? We call them surface because it's a 2D surface, right? So they operate on the principle of exclusion. So if there are gaps in the mesh, anything that is bigger than the gap can't get through. Whereas a depth media filter, we call it depth media because it has depth to it. It's now a 3-dimensional filter, right? Will capture particles of all sorts of different shapes and sizes based on the different pores that are included between the fibers. Now, these fibers are generally either cellulose, that is to say paper, or they might be fiberglass, or there are some, polyamides and some exotic materials as well. Now, the fiberglass type filters are more robust, right, as you can imagine, but the paper style filters are also able to absorb water. So if you want to be able to remove water as well as contaminants, you go for a paper style filter. All right. Now, in terms of measuring the performance of a filter, we have a number of different measures. One is called the efficiency. That's very easy to imagine, right? If I put 100 particles through a filter and 99 are captured, it is 99% efficient. However, we can only state that at a specific micron size. So I would say it is 99% efficient at 5 microns. Then we also have something called the beta ratio, which is literally just the number of particles upstream divided by the number downstream. So in that same instance, if I said 99% efficient, the beta ratio would be 100 divided by 1. So the beta ratio would be 100. That is an escalating kind of scale. So if something is 99.9% efficient, it is a beta ratio of 1,000. 99.99% efficient is a beta ratio of 10,000. So it goes up with orders of magnitude. You might also often hear filter companies say, we are selling a 5 micron absolute filter. That doesn't really mean a whole lot. There are different standards for what an absolute filter means, and no filter captures everything at 5 microns, especially with the depth media, right? So it will allow some amount of them through. All right. So that's a very, very quick summary of all the different types of tests that we can run. Remember, when we're doing oil analysis, we can do it in the field. We can actually now do it inline. There are a whole bunch of live kind of monitoring bits of equipment that we can use now. We have some which are standard tests that are done in a laboratory setting. There are also extended tests which are done in the laboratory, something like MPC, RPVOT, ruler, which gives you a measure of the antioxidants remaining in an oil. These are also done in the lab, but mostly done kind of maybe on a less frequent timescale for things like turbines and compressors. And then you have exception testing. So if you are finding that you have an issue and you need to diagnose the issue, maybe you do something like SEM EDS, which can classify the types of wear particles on a patch, but also give you the actual metallurgy of them, right? Something that we also might want to consider is filter deposit analysis, right? Are you actually, if the filter is capturing a whole bunch of the wear particles, are you actually ever analyzing those wear particles, right? So that's where filter analysis can come in as well. So now that we get our result, we need to also trend them, right? We always need to put our results into context. Yeah, so that's something that's important to do as well. Okay, now let's talk about the different kinds of wear, because we talked about the fact that where materials get generated, how do they get generated? Well, we've got adhesive wear, which is scuffing. There's abrasive wear, which is scoring. You've got corrosive wear and surface fatigue. So what are these? Adhesive wear is literally where we get rubbing action. So we have boundary lubrication and one material adhedes to the other material. Sometimes it's also called scuffing, right? So when we get a collapse of that film thickness, right, often what you will see is like a wiping type wear. And as you can see up on the top right, when we have dissimilar materials, one will generally deposit on the other. Right? So that's a form of scuffing wear, which is very common in things like gears. Then you have erosive wear. So this is where I get particles lodged in, right? And especially in things like plain bearings, you'll see it cut a groove. Now there's two different types of erosive wear: 2-body and 3-body, either erosive or abrasive wear. And that's where you get a contaminant, which is either impinging on the surface, in which case it's 2-body, or it gets connected between two surfaces, and that's 3-body wear. And so this is why particles and contamination are so dangerous, is because they tend to accelerate the rate of wear. Remember that our lubricant film thickness in a hydrodynamic lubrication setting is maybe only 10 microns. And in elasto-hydrodynamic lubrication, it might even be 1 or 2 microns. So that is the kind of size of particle which is damaging to our equipment. Right. We also have corrosive wear. So when we have the buildup of acids, which then corrode surfaces, it makes them softer, which means that they are more likely to be rubbed away. Right. So it's accelerating the wear process. And we also have fatigue wear. So when we go through cycles of loads, right, eventually what we get is crack formation and crack propagation. And when the cracks join up, they basically shoot out a small pit of metal. And so we get something like micro pitting. Okay. All right. Now, lubricant application, as we're starting to get into the home stretch here. So when we apply lubricants, if we are doing it manually, let's say, for example, we are re-greasing a bearing, right? We are returning to the asset once every now and then. And the problem is that sometimes we can overshoot or undershoot the ideal amount of lubricant, right? So we have automation methods which enable us to lubricate on a more frequent basis, but with less volume, which can enable us to kind of thread the needle. Okay, so when we are greasing, right, the most important thing to know about these grease guns is how much pressure they can generate. So a lever action grease gun can generate up to 15,000 psi. So if the grease is not going into the bearing, don't force it, right? Because the amount of pressure that can be generated by a grease gun is way in excess of what a typical bearing seal can handle, right? So that's one thing to know about manual lubrication. And how much should I lubricate? Generally, there are calculators for that, right? So go and have a look at some of the bearing companies. We can also assist with manual lubrication. So there are now tools which are available to us. So, for example, on the right is an ultrasonic grease caddy. You can literally listen to the bearing, and as you are re-greasing, the bearing will quieten down, and you then know that you have applied the correct amount of grease. On the left is something called Grease Boss, which is an Australian company. They've developed a technology which can confirm what grease has gone into the bearing to prevent cross-contamination, and right, whether the correct amount of grease has been put in, right? So it's a sort of a verification system. We also have, you'll have come across auto lubers. These are systems which are sometimes gas powered, sometimes they are spring powered, which are supposed to distribute a certain amount of grease per unit time. Now, the problem with these, right? So generally, we'll go into a plant and there'll be lots of these around in very difficult to reach places, right? Where you don't want to be sending people constantly. The problem is that these are set and forget, and people tend to emphasize the forget, right? So they put one of these auto lubers on and then forget to re-top it up after 1 or 2 years, and you find the bearing has run completely dry and has failed. That's one thing to note about the auto lubers. And then we also have centralized grease systems. Let's say, for example, there are two major types that we'll have to talk through in MLA 1. There's single line series progressive. The easiest thing to remember these by is single line series. So what happens here is every single thing happens one after the other, right? So it happens in series, 1, 2, 3, 4, 5, 6. And what that means is if, let's say, for example, port number 2 is plugged, it means port number 3, 4, 5, and 6 will not receive grease because they are in series. The reason why we might have these, despite the downfalls of it, is it is a cheaper system to install as opposed to a single line parallel system where the failure of one of these lubrication points will mean that doesn't really mean anything. Grease will continue to be distributed to the rest of the grease points, right? Now, one thing to note, just because your grease pump is going does not mean that grease is being applied to the bearing, right? So I often see people will say, oh, but my grease pump was still showing pressure. Okay, but a lot of these grease distributors or grease valves will have like an indication pin which shows whether they are actually firing or not, and it's part of standard practice in maintenance to ensure that those firing pins are actually going. All right. Now, let's talk about lubrication systems, right? Some of these are gravity fed, right? So you might see a lot of these brush style systems where maybe a chain is running through that brush and it is receiving a certain amount of lubricant. Now, the problem is gravity doesn't turn off, right? So it will continue to, even if the machine has turned off or you have a shutdown, oil will continue to be distributed. So the way to get around this is that we do have systems now which can shut off when the equipment shuts off, right? So that's a what do you call it? A gravity-fed lubricator. There are also wick lubricators, where it's like a candle wick, right? Which uses the exact same process as a candle wick, but these can be affected by things like dirt and water contamination. And interestingly, the flow rate is affected by viscosity, temperature, but also the thickness, basically, of the wick that we put in. Now, the advantage of these, super easy to maintain, right? Basically no moving parts. So that's the advantage of using these. They're not as precise, but very easy to maintain. Then we get into something like the constant level oiler. Now, what is this picture trying to demonstrate? A constant level oiler is trying to keep the level of the oil constant inside of the gearbox, inside of this wet sump system. So with gears, generally what we are trying to do is keep the oil level about halfway up the gear teeth. And so therefore the gears will pick up oil and then bring it to the next gear set. A couple of things with these constant level oilers. Number one, right? What we want, can you see the rotation of the blue arrows? We want the oil to be pushing up. Oh, sorry, hang on. My hand's going the wrong direction here. We want it to be pushed in the direction of the constant level oiler. If we had it rotating the other way, right, it would sort of sense that there is a drop in the oil flow and the constant level oiler would keep feeding the system. The other thing that we want to do is we want to be cognizant of the Venturi effect. So as I'm showing this air blowing over the top of the gearbox, right? If we have a breather up there, that can cause the oil level to rise on the inside. So sometimes they actually connect it back to the constant level oiler. All right, so that's constant level oilers. Other different lubrication methods. So maybe we are splash lubricated. So for example, we have this is a wet sump system, right? So there is oil in the bottom of this. Maybe this is a compressor shaft, for example. And we are relying on the pickup of the bearings to spin the oil around the entire system. Now, this is good, right? Up to certain speed factors. Speed factor is dN, so it's the mean bearing diameter multiplied by the rotational speed. Once you get up above certain speeds, you might want to go for something like a slinger ring, which is literally a loose ring which is fit around the shaft, and it will pick up oil from the bottom and it will fling it up to the top. Or there's also oil collars, which are actually fixed to the shaft itself, right? So that's instances where you might want that kind of lubrication. Then we have circulating systems. So this is an example of what we would call a dry sump system, right? So all of the oil is collected in the bottom where it goes to another reservoir. The advantage of circulation systems is that obviously you can filter the oil as it gets redistributed back to the gearbox. Another type of lubrication is mist lubrication, where we generate a fine mist that would go onto the inside of the gearbox. This has a couple of advantages. Number one, right, we know that all of the components are going to get lubricated. But number two, because there's some positive pressure on the gearbox, it's actually going to keep out contaminants like dust and water and all that sort of stuff because there's positive pressure inside of that gear casing. Now, with mist systems, right, generally what happens is you have a misting device which will mix air and oil in a ratio of about, I think it's about 200,000 to 1. So it's almost completely air. That means it is not flammable. So even though you're mixing air and oil, the mixture is not flammable because there is so little oil in it. The disadvantage of mist systems is that they can't pick up contaminants because the contaminants are bigger than the oil droplets. And so therefore it's very difficult to trend things like wear metals. There are two different types of mist systems. One's called pure mist. So that would be an example of a dry sump system. And there is purge mist, which is an example of a wet sump system. Right. When we are spraying any kind of lubricant, for example, in an open gear setting, we want to make sure that there is overlap over the spray patterns, right? So a general way of ensuring that you've got overlap is just to put a piece of paper in front of the spray system and see that there's overlap in the spray pattern. All right, final section, contamination control. The general rule of thumb and kind of like the three commandments is that you're going to keep your oil clean, cool, and dry, right? If you can get those three things right, then you are well on your way to having a really good lubrication program. All right, so when we store and handle lubricants, right, we have to take delivery of lubricants from our supplier. The first thing that we want to do is a paperwork check. We want to check that what turned up on site is what we ordered, right? You'd be surprised at how common it is for the incorrect product to turn up, right? If the incorrect product turns up or the paperwork doesn't check out, we need to put our product into a quarantine area. make sure that no one is going to use that on site. If the paperwork checks out, then we can receive it. There is an opportunity to then filter our lubricants before we put them into storage. So we might want to filter them, right? Kind of self-certify the lubricants and then put them into storage. And we want to use, when it's in storage, we want to use something called a first in, first out principle. So whatever is the oldest stock is being rotated, right? To make sure that nothing, no lubricant kind of expires. When we are taking bulk deliveries, right, this is a little bit different because we are going into a bulk storage tank. So again, paperwork check is super important here. Remember, the people that are driving the truck may not be lubricant professionals. They don't know what's in the truck. And they can often have different compartments that contain different lubricants. And so when they line up from a specific compartment to your storage tank, you want to make ultra sure that it is the correct product, because if you fill your storage tank with the wrong product, that can be a tens of thousands, if not hundreds of thousands of liter mistake, right? So we want to make absolutely sure. One other thing that we might want to do is we might have criteria around testing. So I know a lot of companies, especially in mining, will say when the oil turns up, it needs to turn up with a specific cleanliness code. And if it fails that test, then again, that's a reason to return it to the supplier. Okay. In terms of storage and handling of lubricants, think of it as just good housekeeping practices. We want to make sure that our storage areas are undercover where at all possible. If it's possible to climate control them, that's great, but that's not always possible. And we want to make sure that where possible, we are rotating our stock and we are keeping everything, again, clean, cool, and dry. Now, the issue with water, if we put them outside, is that when drums are rained on, right, as the oil cools down, it tends to suck a vacuum on the inside of the drum, and it can actually draw water into the drum. So that's why we always want to store drums undercover, or else actually on their side. When we have bulk storage tanks, right, that is an opportunity for us to filter the oil before it ever goes into an application. So kidney loop filtration is a really, really good practice. The other thing that we can do is we can put a level sensor on the system, and some of these modern systems can actually talk back to our supplier so they know when to come to top up the system. Bunding is also really important, making sure that the bund can accommodate the volume that is inside the tank so that if there is a leak, right, it is all going to be contained. Okay. When we are storing grease, right, there's a couple of best practices. Most of the time, we want to store them upright. If we are storing them on their side, right, what tends to happen is that there will be a little bit of grease bleed. Remember, what is the purpose of the thickener? The thickener under load is supposed to distribute that base oil out. And so if, for example, we have a grease gun with a grease cartridge inside it, and it is under pressure, right, what we have effectively done is exerted load on the thickener, and so it will constantly be bleeding base oil out of the grease, right? And that can cause the grease to dry out, right? So that's something that we definitely don't want to do. We also don't want to store it in really high temperature conditions. We also want to make sure we're just putting the lids on stuff, right? Very, very easy housekeeping when it comes to storage and handling of lubricants. Finally, we've got color coding systems, tags. We want to make sure that we're putting adequate information on them. What is the kind of lubricant that's in use? What's the viscosity? Maybe there's some information about when to sample and where to sample. When we're using containers, right, the general rule is we want to filter whenever we are doing a transfer. We want to use closed containers, and any funnels that we use are considered consumable for the purposes of our equipment, right? So using funnels, is generally kind of discouraged. All right, that was an unbelievable. I am about to lose my voice, but that was a crazy speed run through the whole of the MLA I program. that basically covers the entire syllabus. Now, obviously, when I actually teach this, it runs over 3.5 days. So I've had to cram a lot of material into 2 hours, but I hope you learned something. And, you know, I really hope that everyone is wanting to sort of like continue their journey along learning. Now, if you do happen to be a lubricant professional that is wanting to sort of level up in your career and sort of collect the infinity stones of different certifications, I do actually have an online program, right? So it's called Lubrication Explained Pro. You can see the website up there. So just for all the people that have spent the time on the webinar, if you actually sign up and use the code webinar, it'll give you 50% off forever for the subscription. I think I've got 10 of those available. So if anyone does want to sign up, now this is a bit kind of deceptive in the sense that it says here $150 a month. That's in Australian dollars. That works out to about $100 a month. But obviously with 50% off, it'll be about $50 a month, and you would be able to take things like MLT1, MLA1, MLA2, VIM, VPR, a lot of those certification trainings. So when FAM asks, how can I learn to become a technical specialist in the lubricants industry? This is a great way to do it. Right? It's a good way to start on this website. There's also a bunch of other tools that are kind of available for you there. If you do want to kind of measure the health of your lubricants program, I've got a system called the Lubrication Excellence program. So the link that is kind of at the bottom of the screen here, excellence.lubrication.expert/scorecard, it's a quick 5-minute survey that can measure you against the ICML 55 standard and give you an idea for how well your lubrication program is going on site. Now, I think I'm going to get the pronunciation of this wrong. Is it Etty Mark? Will this lecture be available after for a refresher? Yes. So I believe that when I finish this, it should just go up on YouTube, right, as a YouTube video, and therefore it'll be accessible to anyone who looks up the channel. Now, we have a couple of minutes left, and I'm happy to stick around. Does anyone else have any questions that they want to ask in the chat? All right, hang on a sec. So we have a question from Bezaleus. Thanks for the amazing webinar. Oh, no problem. Can I ask you an unrelated-ish question regarding the lubricant of bronze graphite plugged bushings? Sure. What is the specific question that you wanted to ask? Okay. While you're typing that, our friend Dennis. So just so you know, Dennis works at Axel Christensen, which is the largest white label grease maker, I guess, in the world. And so really knows his grease. And actually, if you watch the Lubrication Experts podcast, Dennis did an episode on greases. Bear in mind that there is a difference between calcium sulfonate greases and calcium sulfonate complex greases. Yes, absolutely. Calcium sulfonate complex is considered soap thickened. Calcium sulfonate is non-soap thickened. Yes. So I didn't make that distinction when I was talking about the grease thickeners. But absolutely, yeah, Dennis, thanks for definitely pointing that out. Dhanaraj, oh, thanks for coming along. He's asked which book is preferable for the MLA exams. Great question. So there's a bunch of books which I can recommend. Hang on, let me just go into the kind of main view here with... Haha. Okay, so I've got a couple in my... So here's a really good book, Machinery Oil Analysis. I think this is available on the Noria web store, STLE. So the Society of Tribologists and Lubrication Engineers publishes this. Great book, really good reference materials. What else? What else? Do you know what else is a really good book? Is one that I wrote. It's called MLA I. I don't actually have this available yet for purchase, but it is something I'll try to make available through the YouTube channel in a second. So this is actually one that contains a lot of the materials that we've gone through in the lecture. So that I have been giving away as part of my live MLA I programs, and I'm trying to put an MLA II program book together as well. There's also... Here we go. This is Oil Analysis Basics. This is by Jim Fitch and Drew Troyer. So Drew is actually the head of asset health at Anglo American now, and Jim Fitch was the founder of Noria. So this is also a really good primer if anyone is interested as well. So a bunch of different good books there. Okay, I just want to quickly make sure I get to a bunch of the other questions. Richie, thanks for the webinar. Oh, that's you are absolutely welcome. Msevni, do you still recommend self-study aside from what you have just taught to be successful in the MLA I exam? Oh, good question. Okay, so in order to actually sit the MLA I exam, you need to have actually kind of done a course. So when you apply to sit the MLA I exam, it will actually ask you for a course certificate. So you need to have done 24 hours of course materials in order to qualify for the exam. So this is kind of a good primer. It's in 2 hours. It's pretty rushed. So I would advise going and doing a little bit more study before you attempt to sit the exam, because the exam is also not cheap as well. So you want to make sure that you get it first time. What else? Why do barium complex greases have good water washout? That's actually a question that I don't know the answer to, and Dennis actually might have a better answer than me. I don't have any experience with barium complex greases because I've actually never seen them in the market here in Australia. So I've never had exposure to them, never had to use them, and so no, I know very, very little about them. Dennis says, well done. Oh, thank you. Thanks, Dennis. It's always good to see you. Hopefully I'll see you in Dusseldorf maybe later this year. Okay. Oh, okay. So this is back to the graphite and bronze bushings. Some people claim they are self-lubricating. You shouldn't even clean them. Some argue for a low viscosity oil. Okay. So with bushing lubrication, right, most of the time what you're concerned with is like, and this is the case with all kind of lubricants, you're concerned with speed as well as load. So if we are in a circumstance where we have a very high speed bearing, then most of the time, yeah, you're probably going to need some kind of liquid lubricant of low viscosity. If it is a very slow moving bearing, light load, you probably don't need to lubricate it because it has some solid lubricant in it, being that it has it's a graphite impregnated bushing. But if it is low speed and high load, then you're probably going to need some solid lubricants in addition to the graphite that's in the bearing. So that's my opinion on that one. Dave says, great presentation. Thank you. Look forward to talking all things NEOL and ZDDP alternatives. Yeah, so I did make a couple of references to that actually. So Dave is working with me on the copper-based anti-wear additive. So that is an alternative to using ZDDP in things like engine oils and hydraulic oils. So there's a lot of like really good case studies. I'm actually going to publish a video on the YouTube channel about that probably on Friday of this week. So if anyone's interested, you will see that. Dennis says, how does MLA I differ from the FL Cat 1 certification? Okay. That's an interesting question. So MLA I is a exam, so Machinery Lubrication Analyst Level 1 is governed by the ICML, which is the International Council of Machinery Lubrication. It is the equivalent to ISO Cat 1 in the sense that the syllabus for ISO Cat 1, lubrication and MLA 1 are identical. In fact, when the International Standards Organization created the syllabus for condition monitoring level 1 lubrication, they literally copied and pasted MLA 1's syllabus, right? So they are the exact same thing. So you could take all the materials that I just taught and you could sit basically the FL Cat 1 exam. Now, there is the Mobius Institute, which teaches, I think they're calling it FL1, right? Which again, same syllabus, but it is run by the Mobius Institute. My personal opinion on this is that I prefer people to sit MLA1, and that's only because Mobius is a corporate entity, right? They're a profit-seeking company, and so the money that you would get, the money that you would pay to sit the FL1 exam goes to Mobius. Whereas if you sit the MLA1 exam, it goes to the International Council of Machinery Lubrication, who are, in my opinion, kind of giving more back to the industry because they're a non-for-profit that is kind of always trying to do more research and try to elevate the status of lubricants and lubrication. So hopefully that answers that question. Flow. Hey, tribologist in competition motor oil here. I'm not entirely sure what that means by competition motor oil. So, Musveni says, thanks for the answer. Does your MLA 1 training program is sufficient to sit for MLA 1 and 2? Okay, good question. So MLA 2 is obviously the next version of this certification. So it's the next level up. It's the equivalent to ISO Cat 2. On the website, I do have both MLA 1 and the MLA 2 program. So I teach both of those. And there is also an MLA 3, but I haven't put that up on the website yet. So what you've just witnessed here would not be enough to sit the MLA 2 program. This would be a good revision for the MLA 1, though. All right. And I think that's all the questions. Hey, everyone, really appreciate everyone taking the time out. I know that was long. Maybe if you do have a suggestion on what the next webinar should be, I'll probably do it in about 2 months' time. So if you have a specific topic that you would like me to address, whether it's, I don't know, a specific application, I'll probably make it shorter. I'll maybe make it an hour. If it's, let's say, for example, hydraulic oils, or it's something about greases, maybe it's grease application, different application methods. I could also get one of the other lubrication experts. So we have a group of about 10 of us who all specialize in different applications, maybe oil analysis. So let me know what you think would be useful, and we'll go from there. But anyway, I'm going to end the broadcast now. So guys, all thank you so much for participating, and thanks for all the fantastic questions, and I'll see you in the next one.